Good afternoon, everyone. Today I'm going to talk about our work on supporting ACID transactions in hardware for persistent memory systems. This work was done with Vijay Nagarajan, Marcelo Sintra, and Stratus Weiglas. So, as you all might be aware, persistent memory is going to be available in the memory form factor in 2019. This is really important because until now, the only way to access a durable or a persistent storage medium was over this low latency I/O interface, and the access was typically at a block granularity for accessing, disks or hard disks, SSDs or hard disks. With persistent memory, you can have a system where, let's say you have a level of private L1 caches, a shared LLC, which are all volatile, and then at the memory layer, you have persistence or durability. This is really good because programmers now have access to durability at this very low latency load store interface, and it's also accessible at a finer granularity, at typically a cache line. But there are some problems here. So the real question in this case is what happens to the state of data in persistent memory in the event of a system crash? This is known as the crash consistency problem, and people have proposed multiple programming models to ensure that on a crash, the state in persistent memory is either consistent or it can be recovered to a consistent state. ACID transactions is one of the most widely used programming models for this purpose. And in fact, Oracle has argued that providing failure atomicity for certain application scenarios is practically infeasible without using ACID or failure atomic transactions. So here we want to ask the question, how fast can we support ACID? So let us first begin by understanding what we mean by ACID transactions. So at a very high level, ACID transactions provide two properties. One is atomic visibility and another is atomic durability. Atomic visibility can be supported by using logged software transactional memory or hardware transactional memory. And similarly, atomic durability can be supported by using checkpointing, logging in software, or logging in hardware. Since our goal is to support ACID as fast as possible, we consider a combination of hardware techniques, which is using HTM for atomic visibility and hardware logging for atomic durability. So how do HTMs typically provide atomic visibility? So there are multiple commercial HTMs supporting atomic visibility, and they essentially sort of perform two functions. First is version management, which is essentially tracking the read and write set of a transaction, which is done by typically associating read-write bits with cache lines in the L1 cache or some such structure. Another aspect is conflict detection, which is essentially identifying if there are two concurrent transactions trying to modify the same cache line. And commercial HTMs typically piggyback on the coherence protocol to identify such conflicts. In order to commit a transaction, all the HTM has to do is mark the write set as non-speculative and clear the read-write bits. And in order to abort a transaction, they invalidate the write set of the aborting transaction. However, commercial HTMs have a problem, which is that the write set of these HTMs is typically limited to the size of the L1 cache. And this problem gets even worse because of conflict misses, you might not even be able to utilize the full capacity of L1 cache for your write set. To support atomic durability, multiple hardware logging proposals have been published recently, and all of them support or perform the following set of functions. So first is that they write a log entry for every modification that is happening in the transaction in some transaction log in persistent memory. And in order to commit a transaction, all the values are updated in place and the transaction log is cleared. And to abort the transaction, the in-place values are left unchanged, and again, the transaction log is cleared. However, these techniques have either of the two problems. The first problem is either the in-place updates to the data that has been modified in the transaction is in the critical path of commit, which leads to long commit latencies, or it consumes or it requires a very high amount of memory write bandwidth to commit a transaction. So we want to support ACID in hardware by leveraging hardware transactional memory with hardware in conjunction with hardware logging, while providing fast commits, which also minimize the memory write bandwidth consumption And we want to extend the supported transaction size beyond the L1 cache while still maintaining the simplicity of the L1 cache, of the commercial HTMs. Towards this goal, we propose DHTM, which is durable hardware transactional memory, and it uses a combination of commercial HTM and hardware redo log, where it leverages a hardware redo log with a log buffer to reduce the memory write bandwidth requirements for atomic durability, and also enables fast commits. And then it repurposes the hardware redo log in conjunction with a sticky state mechanism to extend the supported transaction size beyond the L1 cache up to the LLC. And at the same time, it still maintains the simplicity of commercial HTMs. So let's first look at how we support, how we design this efficient atomic durability mechanism in DHTM. So the problem, write bandwidth problem with redo log is that for every store in the transaction, a log entry has to be written to the transaction log in persistent memory. Which means multiple stores to the same cache line will generate multiple log entries, which generates a lot of traffic to the memory, to persistent memory. And our solution to this problem is a log buffer, which is a small structure which sits alongside the L1 cache. The log buffer essentially tracks the cache lines that are being modified by a given transaction. And if a transaction modifies the same cache line multiple times, those writes are coalesced in the L1 cache without being written out to persistent memory on every store. And eventually, when a log buffer overflows is when the log entry for the overflowing cache line is returned to persistent memory. So we use this hardware logging mechanism in conjunction with a commercial HTM to support ACID transactions in hardware. So let's look at the state transition diagram of DHTM to understand this whole process better. So on encountering a begin transaction instruction, a transaction would transition to the active state, wherein the transaction can start reading and writing cache lines. After it completes all of its updates and the end transaction instruction is executed, all the log records relevant to that particular transaction are flushed to persistent memory, and at that point, the transaction is deemed to have committed. At this point, even though the in-place values in persistent memory may not have been modified, the transaction is failure atomic, and if there is a crash after this point, all the updates of the transaction can be recovered from the transaction log. And later on, when all the in-place values have been returned to persistent memory, is when a transaction is deemed to have been completed. The important thing here is that as soon as a transaction commits, it can continue executing subsequent non-transactional instructions without waiting for all the in-place values to reach persistent memory. And in case there is a conflict while the transaction is executing, then it's aborted by invalidating its write set and clearing the relevant read-write bits. So let's understand this better with an example. Here we have an L1 cache with a single entry log buffer, and there are read-write bits associated with cache lines. And in persistent memory, we have the in-place values and the transaction log. So we want to execute this small transaction in this case. So on encountering begin transaction, the transaction state is now active. And when a cache line is modified, the address of the cache line is tracked in the log buffer, while the cache line is modified in place with the write bit set. When a cache line is read, B in this case, it's just the read bit is set, and if it's not present, it's brought in the L1 cache. When B is modified, log buffer already had an entry A, and since A has to overflow from the log buffer to accommodate B, a log entry for A is written to the transaction log in persistent memory, and then B is modified in place and its write bit is set. Finally, when the transaction commits, the log buffer is flushed, so the log entry for B is returned to the transaction log along with a commit log record, and at this point, the transaction is failure atomic. Eventually, when all the in-place updates have happened in persistent memory is when the transaction is deemed to have been completed. So given this basic understanding of how DHTM works, let us understand what is the overflow problem in a little more detail. So supporting overflows beyond the private L1 cache into the shared LLC has two problems. First is version management, which essentially requires a global operation on the write set of a transaction. If the version management is happening in the private L1 cache, then it's, the L1 cache is typically small. But if these global operations, which is either invalidating all those cache lines or marking them as non-speculative, have to happen in caches beyond the L1 cache, the overhead is deemed to be infeasible. Another problem is conflict detection. If the overflow is in the shared cache, then we need to maintain additional metadata to identify which cache lines were modified by which transaction, so that on concurrent accesses by different transactions, conflicts can be detected and appropriate actions can be taken. Moreover, supporting conflict detection in a shared cache can also require NAC-based coherence protocols, which significantly increase the complexity of the coherence protocol itself. So with DHTM, we have a twofold solution. For version management, we repurpose the redo log and maintain an overflow list in persistent memory. This overflow list essentially tracks all the cache lines that overflowed from the L1 cache into the LLC. On a commit or an abort, DHTM reads the overflow list to either invalidate or mark those cache lines as non-speculative. So it does not have to perform a search in a huge structure such as the last level cache, but it can read this list and modify individual cache lines or update individual cache lines, state of individual cache lines. For conflict detection, we use a sticky state solution similar to the log-TM proposal, wherein the state of a cache line is not modified in the LLC on an overflow. So let's say core 0 modified a cache line which as part of a transaction, which then overflowed to the LLC. LLC would still show core 1 as being the owner of that particular cache line. So if there is a subsequent access to that cache line from another transaction, conflict can be detected without need for any metadata. And we also avoid NAC-based coherence protocols by restricting this overflow to the last level cache. So let us see how DHTM performs relative to existing solutions. So we compare DHTM with Atom, which is a state-of-the-art mechanism for supporting atomic durability, which uses hardware undo log for atomic durability and locks for atomic software locking for atomic visibility. We also compare DHTM with a combination of two existing proposals, which is an unbounded HTM design log-TM along with Atom, which provides atomic durability. Finally, we look at DHTM, which uses a commercial HTM and hardware redo log. All of the evaluations are for an 8-core machine with a 2-level cache hierarchy that we saw earlier. All the HTMs implement the first writer wins conflict resolution policy. So here we look at the normalized transaction throughput for a set of micro benchmarks which are typically used in applications that require persistence. So, and the results are normalized with respect to a purely software implementation. So both atomic visibility and atomic durability are implemented in software. So Atom, which performs atomic durability in hardware, is able to improve performance by around 30% relative to the software-only design. And log-TM plus Atom further improves that performance by roughly around 10%. But DHTM is 26% better than Atom, which is a state-of-the-art atomic durability solution, and 17% better than log-TM plus Atom, which uses a combination of existing techniques to support atomic visibility and atomic durability in hardware. So the key takeaway here is that although we can leverage existing mechanisms to support ACID in hardware, it's not the most optimum way, and we need to think of new ways to efficiently integrate these two mechanisms in a single solution. So to conclude, persistent memory systems are here, but they need support in the form of crash consistency mechanisms. ACID transactions are a widely used programming model for ensuring crash consistency. And we propose DHTM, which supports ACID transactions in hardware by leveraging commercial HTMs to support atomic visibility and by implementing a bandwidth-optimized redo log implementation for atomic durability. And finally, DHTM also extends the supported transaction size from being L1 limited to the LLC while still maintaining the simplicity of commercial HTMs. Thank you, and with that, I'll be happy to take questions.
Thank you, Arpit. We are now open for questions. Stephanie Slur's Arm Research. That's a very interesting talk. Thanks, Arpit. One quick question. How do you prevent updates that inside the transaction from leaking out to the non-volatile memory early? So how do you prevent them from falling out of the cache and dirtying your persistent memory copy?
Yeah, so similar to existing commercial HTMs, if it overflows, you abort the transaction. So if the write set overflows from the LLC, we will have to abort the transaction.
So you have to track evictions from the LLC, basically?
Yes.
Okay, thank you.
Any more questions? Actually, I have a question. So you talked about atomic durability, and logging is one way. Actually, have you looked into shadow copy, log-free data structures without logging?
Yeah, so that's an excellent question. So there have been existing proposals which use shadow copy to update data, but the thing is it's not very efficient if your updates are happening at a very fine granularity. So if you have something like a file system which is going to update page granular, which is going to perform page granular updates, in that case shadow copying works very well. But with fine granular updates, the cost of sort of 2x the memory for supporting atomic durability is not very feasible.
Thank you. Any more? We have a few minutes.
Sorry, one more question. You mentioned that you're using commercial TM for doing the atomic visibility and you're using the logging for the durability. How do you synchronize? I think there comes that point when you have to make sure that the transaction will commit, from the visibility perspective, and at the same time you have to drain all the log entries into the persistent memory. How do you synchronize these two? That's a fairly tricky part of the design, isn't it? Because you have to do both things at the same time, don't you?
Yes, so the thing is, in order to commit the log, we need to make sure that all of them have reached persistent memory. So you essentially delay the atomic visibility until you have committed the log to persistent memory. So you wait for all the logs to drain out to persistent memory before you make the transaction visible to the others.
And do you have to sort of mark the log as active? So you have to sort of have one last store that tells you when you come.
Yes, so you have to write the commit log record to make sure that
and that has to happen while you're still holding the transaction valid. But at that point, it's sort of, you have to keep the transaction winning all the conflicts because you can't abort it anymore, right?
Yes, so,
okay.
Yeah.
Cool, thank you.
Okay.
If no more questions, let's thank our speaker again.